In the last video, we talked about the Rubik Cube. And in the Rubik Cube, we saw that its group of motion consists of these letters U, B, L, D, F and R, and the typical move was like this. You take any of these letters, suppose I start with D, and you put any power, say I put power T square, follow it by any other letter, say F, maybe F inverse, follow it with B and maybe F again, maybe with D again, and then we can do R inverse. So any such thing is an element of that group. Now here all these letters have interpretations associated with them, but we can actually have the group even if there is no actual interpretation associated with them, and that gives rise to the concept of a free group. A free group starts with some letters. The letters may mean just anything. I can use the letters A, B and C. You can even use just a single letter. And then what you do is you concatenate these letters, as many letters as you like, or their inverses. So for each one of them you have certain symbols which we call inverse, like this. And then you create strings out of all these things, or you may not do anything. So for that I will reserve a special letter which I shall call E. So the elements of the groups are E, which is the identity element, or it could be A, it could be B, it could be C, or any combinations like A, B, 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 C inverse, A inverse, A inverse, then B. So any such string is element of that group, and there is absolutely no condition on these A, B, etc. other than A times A inverse is identity, B times B inverse is identity, and these obvious relations. Other than this, there is no other condition on these things. Unlike our Rubik Cube example where we had L to the power 4 was the identity, because if you turn the leftmost layer 4 times, in that case it returns to its original configuration. We do not have any such restrictions, hence the term free group. Now you might be wondering why the free group will be interesting. The free group is interesting because this is often the starting point of creating a new group abstractly. In fact, we can say that the Rubik Cube group started out like that. We started out with the symbols L, R, U, D, F and B and their inverses together with doing nothing, that is E, and we just had all such strings, but with the added restriction that anything to the power 4 will be the identity, and also certain other relationships that are determined by the geometry of the Rubik Cube. So you start with the free group and put certain restriction to arrive at the particular group that you want. So it is just like sculpting, where you start with a shapeless rock, a shapeless piece of stone, and then you slowly carve it to give it the shape that you want. So free group serves the purpose of that shapeless initial piece of stone. A completely different type of groups may be obtained in the following way. It is called the fundamental group of a surface. To understand the idea, we start with these examples. Here is a piece of cardboard, a rectangular piece of cardboard. Here is another piece of cardboard which is shaped irregularly, and here is a cardboard with a hole in it. Here is another one with a hole in it. Here is one with 2 holes in it. Now if I want you to classify these things, by similarity, then it's natural to say that these two are similar. They do not have any holes. These two have one hole each, and these has two holes each. So these are similar, these and these are similar, and this is different. Now, we want to capture this idea in a more mathematical way. Now, you might be wondering, why do I need any very great thing? Because you just count the number of holes. Here, number of holes is 0, number of holes is 1, and number of holes is 2. Well, things might get somewhat more complicated, like this, where you have a cardboard with a hole, and there is a strip of paper glued here. It enters through the hole and is glued back to the underside of the cardboard. Now, if I ask you to count the number of holes in it, you will be hard put, because this itself behaves like a hole. Because if this piece of paper is connected like this, suppose I connect it like this, in that case you see that there is a hole here, there is a hole through it. And this hole and this hole kind of interacts in a complicated way, so it will be difficult to classify such a piece of thing. And there you need a more systematic way of attacking, and quite surprisingly, the fundamental group helps you to achieve that. To understand this, we start with an example. Suppose we have this card with a hole in it. What I do is I start with any point, just any point on my card. Now imagine that you are an ant. You start your journey here, and you are allowed to move anywhere throughout the cardboard. You move like this. The point is you have to come back to your initial position. So this is what you are doing. This is your path. You go like this and you come back. Now, you can do it in this way, or you can do it in some other way. Suppose I do it in another way, in the following method. Suppose I start like this. I now start like this and come back here. That is also possible. Now I shall say that these two things are equivalent, in the sense that if I consider this as drawn with a string or a rubber band, then I can move the rubber band a little bit until this red rubber band fits perfectly with the black path. So I can move it continuously over the card without ever having to go out of the card, like going through the hole or anything, and I can come here. So I can slowly move this thing here. So instead of doing it, I can move it like this. I can move it like this until I come here. So I can deform one curve continuously into the other. However, if I take my original path in a somewhat different way, like this, then I cannot deform this red path continuously into this black path, because I am going round the hole. I can never move this thing past this hole without leaving the cardboard. My condition is I can never leave the cardboard when I deform one path into the other. So in this case, I cannot do that. So I will say that this path is fundamentally different from this path. Now what I shall do is I shall take each of these fundamentally different paths and consider them as different objects, and these things will quite surprisingly constitute a group. To make a group, of course, we need a binary operation, and this is how I define it. Suppose you give me any particular path. You always start from here and end here, continuous thing. Now you give me any other thing. Suppose I give you this particular path. And then maybe holes here. Possibly there is a hole here. and there may not be any hole here, or maybe there is another hole here, maybe there is yet another hole here, and this is your entire cardboard on which you are working. Now I will give you a binary operation which will combine these two paths into a new path, and it is very simple. So if I call this path A and I call this path B, I am going to define A, B, A followed by B. So my binary operation is this. Suppose I denote it by a star. So A star B is A followed by B in the following way. I start my ant here. I first do A. Now that I am again at this point, I start B. So this is my composite path. And since I allow my paths to be continuously deformed, so this is actually same as doing something like this. I am starting out here, going like this. I am not doing this little groove here because I can do things continuously. And anyway, I am going to return and then start. So I might as well say this and this and this. So this blue thing followed in this direction is my new path, which is, call it C, then this is equal to C. Now if you do B star A, then you will start with this and then follow it up with A. That will be your B star A. You can understand that since all the paths start and end at the same point, so I can always follow one after another, because in order to follow, you need the second path to start from where the first path ended, and that is guaranteed because all paths start and end at the same point. Next, I have to say what is the identity of my group, and that is also pretty simple. The identity is the path which does not do anything, just sits there idly. Since we are talking about two paths being equivalent as long as they can be deformed continuously into one another, so all these things are examples of identity. This is identity. So the idea is, start from here, come back here without going around any hole. That's all. You may just sit here, that is fine, or you may do any of these things. That is also okay. So all these things are actually equivalent and they correspond to the identity element. That is, do not go around any hole. What's an inverse? The inverse is similarly quite easy. So suppose you are starting from here and here is an element and I want its inverse. So you basically want to unwrap around the hole. So its inverse is the same path but traversed in the opposite direction. So that if I do this and then do its inverse, I basically come back to the original point, but this path is not going around this circle. If this point is not clear, let me give you a clearer example. Suppose this is a hole in the surface and this is a path whose inverse I am computing. Suppose it is A, then its inverse is A inverse, the same path traversed in the opposite direction. I am going to convince you that A star A inverse is indeed identity. So A, I first do this, this is this, I arrive here and then I am doing A inverse, I am coming back like this. So you see this path, this is A in star A inverse, this path has no hole at all inside it. Remember, this hole is outside the path. My new path is this loop that bends back on itself. So since this interior of the loop is free of any holes, so this is actually same as identity. Now it would come as a surprise that all these things will actually form a group. And this group will be different for different types of surfaces, whether you have holes in them or you do not have holes in them. And we'll say the two surfaces are basically the same in the same class if they have the same fundamental group, and they belong to different classes if they have different fundamental groups. So suppose that I have these two pieces of cardboard and I want to understand that they are actually different using their fundamental groups. So I start with a point here, a point here. Now, whatever path I take here naturally can be deformed into just that singleton point. So everything here is equivalent. All paths are equivalent. They may be continuously deformed one into the other. As a result, only the identity element is present in that fundamental group. In this case, a path may be like this, which is an identity element, or a path may be around that hole. So if I call this A, then obviously everything that traverses the hole in this clockwise direction will be equivalent to A, and if I traverse it in the counterclockwise direction, I have this. As a result, my fundamental group will be this in this case. Observe that this has nothing to do with the shape of the cardboard or the shape of the hole. It just works with the number of holes. And you can apply the same idea to classify even more complicated surfaces like a torus. So here you can take a torus and you can take different types of loops. You can go like this and observe that this can never be deformed into just identity thing. You can take a loop like this, you can take a loop that goes around the torus like this, and accordingly you will have a group which is different from the group of this torus which has a beach in between. And you can take more exotic stuffs where there are holes and you have got strips of paper passing through the hole and doing more complicated stuff. And you can classify all such surfaces using their fundamental groups.